In the deep quiet of the universe, galaxies drift, collide, and reshape the fate of everything around them. In Space Dream's documentary, we journey beyond the visible glow of stars to explore the hidden forces that sculpt cosmic boundaries, the slow dance of gravity, and the vast scales of time that redefine entire galaxy groups. Each episode invites you to travel from the faint outskirts of merging giants to the silent edge where gravity yields to expansion. If you're fascinated by the mysteries of space and the calm beauty of the cosmos, make sure to like this video and subscribe to Space Dream's documentary. Turn on notifications so you never miss a new voyage into the universe's most profound and peaceful wonders. A faint smear of light hangs in a quiet sky too soft to feel urgent. The Milky Way and Andromeda move toward each other, and the approach is already underway. At this distance, the two spirals look like separate islands. Their edges seem clean and finished. The darkness between them looks empty. The emptiness is not empty. In that region, gravity quietly connects what appears separated. The connection is slow. It is steady. It does not require a sudden moment to begin. A long oval glow sits against black. Its center brightens gently. Its outer light thins into a pale gradient. A darker lane cuts through parts of the glow, like a thin thread of soot. The shape is tilted. The tilt makes the disk look like a soft lens. The Milky Way is not seen from outside here. It is felt as a wide band of star haze. It is suggested by the thickness of background starlight. It is implied by the way dust dims and scatters that light. Two large spirals occupy the same quiet neighborhood. This neighborhood is called the local group. It is not a cluster with tight symmetry. It is a loose association shaped by shared gravity. It holds a few large galaxies and many smaller ones. The smaller members trace paths that are gentle and long. They do not move in straight lines for long. Their roots curve. Their roots drift. Their roots respond to mass that cannot be seen directly. That unseen mass is the deeper stage where the story happens. A halo surrounds each large galaxy. It is not a bright shell. It is a broad region where gravity is stronger than light suggests. Dark matter is the name used for this unseen mass. It is matter that does not shine and does not block light well. It still has gravity. It still adds weight to a galaxy. It still shapes motion across vast distances. The halos are much larger than the visible disks. Their edges do not have sharp borders. Their influence fades outward like warmth fading from a stone. When two halos approach, the overlap begins early. The first contact is not a collision of bright stars. It is the overlap of invisible influence. This is the first small unlock. The coming encounter begins long before any bright structure touches. A light year is distance light travels in 1 year. It is not time. It is a way to speak about scale. A light signal would take 1 year to cross 1 light year. In a room, a whisper crosses in a moment. In intergalactic space, even light takes years to move between nearby points. Andromeda lies about 2.5 million light-years away. This is like 2 lanterns across a plain so wide that a spoken sound never arrives. The comparison stays gentle. It keeps the number from turning into pure abstraction. The distance sounds enormous. The approach still happens. The approach can be measured as a shift in the way light is stretched. Light behaves as a ruler only in a calm sense. It carries information in waves. The waves can lengthen if a source moves away. They can shorten if it moves closer. A signal would arrive with its pattern slightly shifted. That shift reveals a line of motion along the line of sight. It does not reveal the full path across the sky. Here lies a limit of observation. The sideways motion is harder to measure. It is small against a far background. It requires watching tiny shifts over long time. It requires precision that approaches the edge of what can be separated from noise. Small errors in distance and sideways drift change the timetable. They do not change the direction of the story. Gravity makes the direction stable. That is another small unlock. Uncertainty softens the schedule, not the outcome. The visual scene returns to the oval glow. The center of Andromeda brightens into a rounded bulge. The bulge is smoother than the disk. The disk holds hints of structure. Dark lanes trace gentle curves. Those lanes are dust. Dust does not need to be thick to matter. A thin layer can scatter and absorb light. It draws shadows across a galaxy that spans more space than intuition likes. The shadows are not sharp, they are gradients. They soften at the edges. The soft edges speak of depth. Some dust lies in front of bright stars. Some dust lies behind them. The brightness changes with position. The disk is not a flat painting. It is a layered sheet with thickness and texture. In that sheet, stars orbit the center. The orbits are not rigid grooves. They are paths shaped by mass. The disk rotates. The rotation is not seen as spinning in a glance. It is inferred. A pattern would reveal itself through careful measurement over time. The quietness is an illusion created by scale. A leaf can drift across a still pond in silence. The drift can be steady. The drift can still be real. The galaxies drift like that, but on a scale that turns motion into patience. The local group space is not filled with constant collisions. Most of it is thin, gas is sparse, stars are far apart. When the galaxies finally overlap, stars rarely meet directly. The main reshaping comes from gravity and from gas flows. This is a calming detail. A collision at galactic scale is not like stone striking. It is like two fog banks passing through. The fog banks change shape as they overlap. The overlap can compress and stretch edges. It can pull long streams from outer regions. It can thicken some lanes of gas. It can leave other regions quieter. The first sign of the approach is not a crash. It is a tug on the outskirts. The outskirts are faint. They are easy to miss. They still matter. The outer halo responds first. The outer halo is where the pull begins to rearrange orbits. The disk follows later. This sequence keeps the coming event gentle. It shows the order in which structure yields. A long dim envelope surrounds the bright parts. It fades into black without a clear boundary. That fading is a physical detail. It is a gradient of density. It is a gradient of gravitational influence. The Milky Way's own halo extends similarly. Where the two halos overlap, the combined gravity deepens slightly. Orbits of smaller galaxies can shift. Paths of diffuse gas can bend. The neighborhood's shape can change without any bright flare. The local group looks like a handful of lights scattered across night. The true structure is like a faint pressure field around each light. That pressure field cannot be seen directly. It can only be inferred from motion. In that inference lies another limit. Models must assume how dark matter is distributed. Models must assume how much mass lies in the halo. Different assumptions still fit the same sparse measurements. The uncertainty is not failure. It is a reminder that the deepest mass is silent. The silence does not mean absence. It means the story is read through consequences. The approaching motion is a consequence. The future merging is a consequence. The present calm is a consequence. The scene holds steady on the distant oval again. The light remains soft. The dust lanes remain like thin charcoal strokes. The black around them remains vast. In that black small companions drift. Some are faint smudges of their own. Some are star streams stretched like loose fibres. Those fibres hint at past encounters. They hint at tides. Tides are gentle forces that vary across an object. One side is pulled slightly more than the other. Over time, that difference stretches structure. It can draw arcs from outer edges. It can turn a round glow into an elongated haze. It can create shells and ripples. The ripples are slow. They are graceful. They are written in stars across tens of thousands of light years. A scale shift settles in. In a second, a grain of dust falls a small distance. Over billions of years, galaxies fall toward each other across intergalactic space. The same kind of pull operates. Only the distances change. Only the times change. The quiet does not change. The next step is to map this neighborhood more carefully. The local group's members and motions set the frame. The coming sections move from this calm overview into the structure of the group and its hidden mass. A neighbourhood in deep space rarely has a fence, yet it still has an edge. The local group holds together because its gravity is stronger than the outward drift of expansion in its core region. At this distance, the scene looks sparse. A few bright spirals stand out. Many smaller galaxies appear as faint knots. The darkness between them is wide. The wide spacing makes the group feel unconnected. The connection is carried by motion. The first small unlock is simple. Membership is not decided by brightness or by shape. Membership is decided by whether paths curve back inward over very long time. A slow visual anchor settles on a field of tiny dim galaxies scattered across black. Each looks like a soft grain of light. Some sit in loose strings. Some sit alone. The strings are not straight. They bend gently as if laid along a shallow contour. In that region, gravity behaves like a landscape. It does not need hills of rock. It needs only mass. Every galaxy adds a slight slope to that invisible terrain. Dark matter adds most of the slope. The bright stars mark only the highest points. The rest of the landscape extends far beyond what is seen. The main idea takes a quiet form. The local group is less like a cluster of objects in a box. It is more like a drainage basin in slow motion. In a drainage basin, water that falls inside the divide eventually gathers toward the same lowland. Outside the divide, it drifts to a different river. Here the divide is not a ridge of stone. It is a boundary where outward expansion and inward gravity balance. Inside paths tend to remain bound. Outside paths tend to separate. This is an analogy that stays gentle. It also explains why the edge is hard to draw. The boundary is not a wall. It is a surface of balance. It can be uneven. It can shift slightly as mass moves. A small payoff lands here. A galaxy can sit near the group and still not belong. It can be close in distance, yet its motion carries it away. The visible distance is only part of the story. The direction of the motion is the other part. Motion has components. One component lies along the line of sight. Light behaves as a messenger that carries that component as a subtle stretch or squeeze of its waves. The sideways component is quieter. It appears as a tiny drift across the background. Over short time it looks still. Over long time it leaves a trace. The trace is measured in angles so small that they blend into uncertainty. This is a limit of observation. The sideways drift is hard to separate from the blur of distance errors. The farthest and faintest members suffer the most. A small error in distance becomes a large error in true speed. Models must fill the gaps. They must assume how dark matter spreads in each halo. They must assume how much mass lies between the big galaxies. Different assumptions can fit the same sparse set of motions. The uncertainty does not erase the basin. It softens the exact outline of its divide. A new visual anchor glides in. The field of faint galaxies becomes a slow map of currents. Some are arranged as if carried along invisible streamlines. A few appear stretched into very thin arcs. Those arcs are tidal debris. They look like pale ribbons that fade at the ends. The fading is a gradient of density. It is a physical detail tied to the process. Tides do not pull uniformly. One side of a small galaxy feels a slightly stronger tug than the other. Over time, stars are teased outward. The teased out stars form streams. Streams mark the flow of gravity like dye in a slow river. Another small unlock follows. The local group is not defined only by what it holds now. It is also defined by what it has gently pulled apart before. The streams are quiet evidence of past encounters. The group's largest members dominate those encounters. The Milky Way and Andromeda are the main wells. A third large member, a bright spiral nearby, adds another slope to the basin. Its presence matters even when it seems distant. The centre of mass of the group does not sit inside any single galaxy. It lies in the space between the largest contributors. The centre is not a bright point. It is a balance point in the landscape. If mass were marked by contours, the contours would tighten around the big galaxies. They would also sag toward the middle. That middle is where the group's shared pull is strongest. The number that anchors this section arrives softly. The local group spans about 10 million light-years across, which is like a silence so wide that a light signal needs 10 million years to cross it. The comparison stays natural. It turns the number into a travel time for a beam. It avoids dense digits. It also creates a scale shift. In a second, a faint photon crosses a few 100,000 kilometers. In 10 million years, it crosses the whole neighborhood. In that immense span, the galaxies still drift. They drift slowly. They drift predictably enough to trace the basin. The basin is not static. It responds to passing members. It responds to mergers among the small ones. It responds to the slow rearrangement of the halos. Yet the overall shape remains. A further payoff settles in. The local group is not a random scattering. It is a system with a gentle hierarchy. Big wells guide small paths. Small paths reveal the wells. The relationship is calm and circular. The physical picture becomes more concrete. A halo is not a sharp shell. It is a thick layered region where density declines outward. Near the center, the density is higher. Far out, the density thins. The thinning is gradual. The thinning makes edges uncertain. The thinning is why the group's boundary is a surface rather than a line. The group's edge is sometimes described as a zero-velocity surface. The phrase means a boundary where inward fall and outward expansion cancel. It is a definition in plain form. The idea is simple. Inside the net, drift tends inward. Outside the net, drift tends outward. The phrase is useful because it emphasizes motion over appearance. It also emphasizes limits. That surface cannot be seen directly. It is inferred from velocities that are themselves uncertain. It depends on distance estimates that can be biased. It depends on assumptions about unseen mass between members. This is the limit passage stated gently. The edge is real as a concept. The exact contour is not fixed by direct sight. The section returns to the main visual anchor. The faint galaxies sit like dew on an invisible slope. Some dew beads would slide toward one basin. Others would slide toward another. The slope is not steep. It is enough. The same quiet rule operates across the group. Over billions of years, slight differences add up. Paths that barely curve become arcs. Arcs become captures. Captures become mergers. The long horizon makes the present feel still. The stillness is a scale effect, not a lack of motion. The next step moves from the basin to the main river. The Milky Way and Andromeda carry most of the group's story, and their approach begins to take shape in detail. A spiral galaxy looks like a quiet picture until the mind remembers it is moving. A rotating disk holds together because its gravity and its motion balance. At this distance, Andromeda appears as a tilted oval with a bright center. The outer light thins into a smooth gradient. Dark lanes curve across the glow. The lanes are not painted lines. They are dust concentrated in a thin layer within the disk. Dust is small. Its effect is large. A thin veil can dim a bright region. A thin veil can also scatter light softening edges and blending fine detail into haze. The first small unlock arrives early. The dark lanes are not holes. They are shadows cast by material that sits in front of starlight. A slow visual anchor holds on one curved lane as it arcs inward. The lane is slightly uneven. It thickens and thins like a ribbon laid across a lamp. Near the center, the bulge glows smoother. It looks rounder than the disk. The bulge suggests many stars packed into a dense region. The disk suggests a flatter spread. This difference is a physical shape. It matters because shape reveals how mass is arranged. Mass arrangement guides rotation. Rotation is the section's first core concept. Rotation here means many stars orbit the same center. The orbits do not need to be identical. The overall pattern still forms a disk. The second core concept is the rotation curve. A rotation curve is speed versus distance from the center. The definition stays short. It frames the next unlock. In a simple picture, inner parts should orbit faster. Outer parts should orbit slower. That simple picture would match a disk where most mass sits near the center. In many spirals, outer parts still move fast. The speed does not fall as much as expected. This gentle mismatch is the quiet doorway to dark matter. A third concept enters only as needed. Dark matter is unseen, mass-shaping gravity. It avoids a heavy roll here. It supports the curve without stealing attention. The scene returns to the tilted disk. At this distance, the spiral arms are subtle. They appear as broad bands of slightly brighter texture. They are not sharp lines. They are density waves. That phrase needs care. A density wave is a moving crowd pattern in a disk. It is not a fixed set of the same stars. The 1-2-1 rule stays calm. A wave in a crowd shows where bodies bunch up. A spiral arm is where stars and gas bunch up briefly. It matters because the bunching helps explain the arm's shape without freezing it. A new visual anchor arrives. The disk is imagined as a wide sheet of fine mist. In that mist, faint ridges appear where the mist is slightly thicker. The ridges curve gently. They do not spin like solid spokes. They drift as patterns while the material flows through. This is a second small unlock. Spiral arms can persist as patterns even while individual stars move on. The dust lane seen earlier often sits along an arm. Dust and gas collect where the crowding is stronger. The dust then traces the arm with shadow. The shadow's a boundary detail. One side of an arm looks slightly brighter. The other side looks slightly muted. The muted side is where dust lies in front. Light behaves as a traveller here. It passes through the dust and loses some brightness. It also scatters, creating a softer edge. The difference in sharpness can hint at which side of the disk is nearer. That hint is delicate. It requires careful modelling of geometry. This leads to the limit passage. The tilt of Andromeda makes depth hard to read. Some structures overlap along the line of sight. Fine details blur together. Even when a dust lane is seen, its exact height above the disk is uncertain. Its thickness is uncertain. Its true distance from the centre is uncertain. The measurement depends on resolution and on how light is absorbed in different wavelengths. At great distance, the smallest features merge into one. The disk becomes a smooth wash. The lane becomes a broad shadow. A small payoff follows. Even with limits, the large-scale pattern still speaks. The overall gradient of brightness reveals that the disk extends far beyond the brightest core. The disk's faint outskirts matter because rotation is measured there. The outer disk is where the rotation curve shows its most telling shape. The one main number arrives with care. Typical orbital speeds in a large spiral are about 200 kilometers per second, like a fast jet circling a continent without ever landing. The comparison stays everyday and quiet. It turns speed into a familiar idea of travel. It also creates a scale shift. In a second, that speed carries material a few hundred kilometers. In a million years, it carries material across a vast arc of the disk. Over billions of years, it builds repeated passages that smooth some structures and sharpen others. The disk does not tear apart because gravity holds it. The motion does not stop because gravity does not erase angular momentum. The balance is steady. The balance is what makes a spiral a long-lived form. The analogy for the whole section settles in now. The galaxy behaves like a slow-glowing carousel, not because it is a rigid platform, but because the motion is organized around a center. The carousel image is unique here. It emphasizes circular paths without invoking any human presence. It frames rotation as gentle repetition. It also avoids hard mechanics. The physical details remain anchored in dust and gradients. A second visual anchor follows. The bulge is seen as a bright pearl embedded in a translucent shell. The shell is the disk. The pearl is not separate, it is just denser. The shell fades outward. The fade is smooth. The smoothness tells a story. It suggests a large halo of gravity beyond what light shows. This is another small unlock. A rotation curve that stays high implies extra mass in the outskirts. Extra mass does not need to shine. It only needs to pull. That pull keeps outer orbits fast. It also shapes how Andromeda responds to the Milky Way's distant tug. A gentle transition begins. The disk's organised motion makes the future encounter less like a crash and more like a dance of orbits. The next section shifts from internal rotation to the shared motion between galaxies where approach and sideways drift set the path. A closing distance can feel like stillness when the scale is vast. The Milky Way and Andromeda move closer because their shared gravity bends their paths inward. At this distance, the approach is not a bright spectacle. It is a quiet change in separation. It is also a quiet change in direction. Two motions matter here. One is the motion along the line of sight. The other is the sideways motion across the sky. The first can be read from light. The second is harder to hold. The first small unlock arrives quickly. An approach does not require pointing straight at each other. A curved path can still end in a meeting. The scene begins with a thin band of starlight and dust that hints at the Milky Way's plane. It is a soft, uneven glow. Dark patches lie within it. Those patches have blurry edges. The blur comes from scattering and from layered dust at different distances. Beyond this band, Andromeda sits as a pale oval. Its centre is brighter. Its outer rim fades into a gentle gradient. The rim is not a sharp border. It is a slow thinning of starlight. That thinning is physical. It shows how the visible disk becomes faint before it ends. It also hints that the gravitational influence extends farther than the light. The section's first core concept is radial velocity. Radial velocity is speed toward or away along the line of sight. The definition stays simple. Light behaves as a wave that can be stretched. When a source moves away, the wave arrives longer. When it moves closer, the wave arrives shorter. The shift is small. It is consistent. It can be measured and compared. This is where a calm number can sit. Andromeda approaches at about 100 kilometers per second, like a fast wind crossing a country in under a day. The comparison keeps the number grounded. It also creates a scale shift. In 1 second, that speed covers a long highway's worth of distance. In 1,000,000 years, it covers a span that would swallow a galaxy's disk many times. In billions of years, the same steady drift becomes a change in the local group's map. The next visual anchor holds on a long invisible line between the two galaxies. Along that line, faint intergalactic space remains mostly empty. There is no bright bridge. There is no continuous band of stars. There is only a hint of a shared haze where halos overlap. That overlap is too dim to see in a simple image. It exists as a gravitational fact. This is another small unlock. The first stage of the encounter is already happening in the unseen mass. The visible disks remain far apart. The halos begin to mingle earlier. The second core concept is proper motion. Proper motion is sideways drift on the sky. It is not a speed in space by itself. It is an angle changing over time. A small angle can hide a large sideways speed if the distance is great. This is the central limit passage. At Andromeda's distance, the sideways drift is so tiny that it blends into uncertainty. The background is crowded with faint points. Their positions are not perfectly fixed. The galaxy's own internal structure shifts subtly with rotation. Dust lanes change apparent contrast as light blends. These effects complicate a clean measurement. A model must separate the galaxy's internal motions from its drift as a whole. The separation depends on resolution and on long baselines of time. The result is a range, not a single line. The range matters because sideways motion changes whether the path is a near miss or a deeper encounter. Yet even here the calm conclusion remains. Within reasonable ranges, the two large halos pull strongly enough that an eventual merging remains likely. The scene returns to the sky as geometry. Imagine a long, slow curve traced through space. The curve is not a straight chord. It is a bending arc shaped by gravity. The analogy for this section takes a quiet form. The approach resembles two slow-moving raindrops on a window drawn together by a thin film between them. The film is not seen directly. It is felt through the way the drops curve inward. This image stays gentle and unique. It also avoids impact. It emphasizes drift and curvature. The raindrops do not leap. They glide. Their edges change shape as they get closer. That changing edge corresponds to tidal influence in galaxies. The outer parts feel a different pull than the inner parts. The outer parts respond first. Even now, long before visible contact, the faint outskirts can begin to shift. The physical detail appears as a very faint stellar halo around each galaxy. It is not uniform. It can be lumpy. It can hold shells and streams. These features are low contrast. They fade into the black. They are easy to miss. Their softness is part of the story. Soft edges reveal that the halo is not a rigid boundary. The softness is also why the edge is difficult to measure. A small payoff follows. If the halo edge is uncertain, the mass is still present. The tug can be inferred from how smaller companions move. Their paths act like floating seeds in a breeze. They reveal currents without making them visible. The local group's smaller galaxies are not just decoration. They are tracers. Some orbit the Milky Way. Some orbit Andromeda. Some drift between. Their distribution and their speeds help estimate the mass of each halo. Those estimates feed back into the predicted path of the big pair. This feedback loop is another quiet unlock. The collision story is not told by a single number. It is told by a web of motions that must agree. The web is imperfect. It still converges on a future encounter. The scene narrows again to light. Light from Andromeda travels for millions of years. It arrives carrying both an image and a Doppler shift. The image shows a disk with dust lanes. The shift shows approach along the line. These two kinds of information sit together. One is spatial structure. One is motion. Together they form a calm map. The map is not complete. The sideways motion remains the uncertain part. The uncertainty is not dramatic. It is like trying to judge a distant boat's drift by eye on a hazy day. The boat moves. The movement is real. The exact angle is hard to pin down. Over a long time, the path reveals itself. Another visual anchor arrives near the end. Two faint ovals sit in a dark field. Between them, a very subtle haze suggests overlapping influence. Around them, a sprinkling of small galaxies marks the basin of the local group. The whole scene feels almost static, yet motion threads through it. The motion is slow enough to be restful. It is also strong enough to be inevitable. The next section moves from the pair's relative motion to what shared gravity builds around each galaxy. Halos and tides begin to set the order of events long before any bright structures meet. An edge can be invisible and still decide the shape of everything that follows. The halos of the Milky Way and Andromeda overlap long before their bright disks come close. At this distance, a halo is not a glowing shell. It is a wide region where gravity remains strong while light fades away. The first small unlock is quiet. The coming encounter begins in the outskirts, not in the bright centres. A slow visual anchor opens on a dim spherical haze around a spiral. The haze is barely brighter than the black behind it. It has no sharp boundary. It thins outward with a smooth gradient like breath on a cold surface that fades at the edges. Within this haze, a few thin arcs appear. They are star streams. They curve gently. They fade at the ends. Their fading is a physical detail tied to density. It shows stars spread out along an orbit not packed into a compact body. The section holds to three concepts. The first is the halo itself. The second is tidal force. The third is dynamical friction. A halo is the extended mass around a galaxy. It is mostly dark matter. It also includes a faint population of stars and thin gas. The halo matters because it is the first region to meet the other halo. In that region, gravity from the approaching partner is not uniform. Tidal force is the difference in gravity across an object. The definition stays short. If one side is pulled slightly more, stretching begins. If one side is pulled slightly less, squeezing begins. A small galaxy inside a halo feels this difference strongly. Its outer stars are lightly bound. They can be peeled away. The peeled stars form streams that wrap around the host like pale threads. This is another small unlock. Streams are not decorations, they are maps of gravity written in starlight. A new visual anchor arrives around the streams. A faint ribbon curves across black. It has a brighter knot near one end. It widens and narrows along its length. It looks like a trail of fine sand poured in a slow arc. The knot is the remnant core of a small companion. The ribbon is the stripped material. The ribbon's width carries information. A narrow ribbon suggests a colder, more orderly orbit. A wider ribbon suggests more internal motion before stripping. These details are subtle. They also reveal a limit of observation. Many streams are so faint that their brightness blends into background variations. Their edges are uncertain. Overlapping streams can be confused with each other. The line of sight can stack structures on top of one another. Even when a stream is detected, its distance along the line of sight is hard to pin down. The inferred orbit depends on assumptions about the halo's shape. A spherical halo gives one path. An elongated halo gives another. The limit is not dramatic. It is a gentle reminder that the halo is read through faint traces, not through direct sight. This section's main number appears with care. A typical dark matter halo extends several 100,000 light-years from its galaxy, like a quiet shoreline that reaches far beyond the bright city lights. The comparison keeps it grounded. It also sets a scale shift. In a second, a photon crosses a small gap. In hundreds of thousands of light-years, a halo spans a region that makes a disk seem like a small, bright island. This shift changes intuition. It explains how halos can overlap while disks remain distant. The overlap is not a single moment. It is a gradual interpenetration of two low-density regions. In that overlap, tides begin to act. The outermost parts feel the partner's pull first. Orbits in the halo begin to deform. Some become slightly more elongated. Some tilt. Some precess slowly changing orientation over time. This is a small unlock. The first changes of the encounter are changes of orbit, not changes of brightness. The third concept enters now. Dynamical friction is drag from gravitational wake. The definition stays within 12 words. A massive object moving through a halo perturbs surrounding matter. The perturbed matter forms an overdense region behind it. That overdense region pulls back. It slowly drains orbital energy. The idea is calm. It is like moving through a field of loose snow where a trough forms and resists motion. This analogy is unique here. It avoids sharp impact. It conveys slow loss of momentum. It also keeps the process physical without invoking human tools. The effect matters because it makes the approach deepen. Even if a first pass is not perfectly centered, dynamical friction tends to shrink the orbit over time. Each pass can become closer. Each pass can become slower at closest approach. This makes merging more likely. Another visual anchor forms. Two broad halos overlap like two faint clouds meeting. Where they overlap, the combined density is slightly higher. The overlap region is not bright. It is only a deeper part of the gravity field. In that deeper field, small companions can be redirected. A dwarf galaxy passing near the overlap can have its orbit bent. It can be captured by one host. It can be flung onto a new path. The dwarf's outer stars can be stretched into a longer stream. This is another small payoff. The overlap region is a quiet workshop. It rearranges the smallest members first. It also prepares the stage for the giants. The physical detail returns to gradients. The halo does not end. Its density just falls. The fall is smooth, not stepped. That smooth fall is why edges are fuzzy. It is also why predictions vary. If the halo is heavier in the outskirts, the pull between galaxies is stronger. If it is lighter, the pull is weaker. The current estimates of halo mass depend on tracer motions that are limited in number. They depend on assumptions about equilibrium. They depend on whether the halo is perfectly relaxed or still settling from past mergers. This is the limit of model passage stated clearly. The unseen mass must be inferred from incomplete samples. Incomplete samples can bias the inferred shape, yet the broad picture holds. Halos are large. Halos overlap early. Tides begin in the faint outskirts. Dynamical friction quietly reduces orbital energy over long time. The section returns to the stream ribbon once more. Its faintness is restful. Its curve is smooth. It suggests motion without urgency. It also suggests memory. The halo holds the record of past encounters in these delicate structures. The Milky Way's halo contains such records. Andromeda's halo contains such records. When the two halos begin to overlap more deeply, the records can be disturbed. Streams can be heated. They can thicken. They can blur into a smoother halo. This is a small unlock that softens the future. A merger does not only create new structure, it also erases some old fine detail, turning sharp ribbons into broader haze. The next section moves from halos as extended mass to tides as sculpting force. The focus shifts from the existence of overlap to the specific ways outer edges stretch, fold, and respond before any bright disks meet. A gentle pull can shape an edge without touching the center. Tidal forces begin sculpting galaxies while their bright disks still look separate. At this distance, the first changes are subtle. They appear in the faint outskirts. They appear in the way a halo's smooth gradient gains faint ripples. The first small unlock is clear. A merger starts as a change in orbit shapes, not as a collision of stars. The main visual anchor opens on the outer rim of a spiral disk. The rim is dim. It is not a sharp line. It is a thin wash of starlight that fades outward. Beyond it, a halo lingers as an even fainter haze. In that haze, a narrow arc of stars curves like a crescent. The crescent is not centered on the galaxy's core. It floats slightly offset. Its brightness declines along its length. That decline is a physical gradient. It hints at material spread out by differential pull. The section holds to three concepts. The first is tidal force. The second is tidal tail. The third is pericenter. The tidal force is the change in gravity across an object. It is not a new kind of force. It is gravity with a gradient. One side of a galaxy feels a stronger pull than the other. Over time, the mismatch stretches orbits. Tidal tail is a long stream drawn from the outer parts. It is made of stars and gas that become loosely bound. Pericenter is the closest approach in an orbit. The definition stays short. It is the moment when the two galaxies pass nearest on their first swing. The structure of the encounter depends on how close that swing is. It also depends on the angle between the disks and the orbit. Those details are hard to see from far away. That leads toward the limit passage later. For now, the story stays on edges. The outskirts respond first because they are lightly held. Inner regions are deeper in the gravity well. Outer regions are closer to escape. This is the second small unlock. The first visible signatures of an approaching partner are often found in the faintest light, not in the brightest. A new visual anchor arrives. A thin band of dust lies along a spiral arm. It casts a soft shadow with blurred edges. The shadow widens slightly in one region. The widening suggests compression. Gas clouds in a disk can be nudged inward by tides. They can also be stretched along an arm. The dust lane becomes uneven. It looks like a ribbon gently tugged at one end. The tug does not rip it instantly. It changes its curvature. It changes its thickness. Light behaves as tracer here. It highlights the dust by what it hides. The darkness is a shadow, not an absence. This keeps the imagery physical and calm. The first main number appears with care. The first close pass is expected in about 4 billion years, like a slow tide that takes longer than any mountain's weathering. The comparison holds to deep time. It also creates a scale shift. In a second, a grain of dust falls a small distance. In 4 billion years, a galaxy's outskirts can be pulled into long arcs. The scale shift is gentle. It does not demand urgency. It invites patience. The path toward pericenter is long. The effects begin early. As halos overlap, the combined gravity field becomes slightly deeper between the galaxies. Small companions drift through this region. Their orbits can be changed. Their outer stars can be stripped. These changes create additional streams that wrap around the hosts. The streams form a kind of lacework in the halo. The lacework is faint. It is not symmetrical. It is the record of many small tugs. The lacework also becomes the raw material for future tails. When a major tidal event happens, the existing streams can be heated. They can thicken. They can blend into a smoother glow. Another small payoff sits here. Tidal features are temporary in detail. The broad mass remains. The fine structure can be erased and rewritten. The section now explains why tails form. During a close pass, the partner's gravity can add energy to some outer orbits. Those orbits become more elongated. Some become unbound. The unbound material flows outward along the direction of the pull. It forms a tail. The tail is not a rigid arm. It is a stream of many objects on similar trajectories. Its shape is guided by the orbit geometry. It can curve. It can split. It can develop knots where density is slightly higher. The knots are not necessarily separate galaxies. They can be clumps of stars and gas moving together briefly. The physical details remain consistent. Tails have edges. Their edges are not sharp. They fade outward. They show gradients in density and brightness. They can have a leading side that is slightly sharper. They can have a trailing side that is more diffuse. These differences come from how material spreads in phase space, not from impact. The story stays restful by emphasizing slow flows. Another visual anchor arrives. A long tail arcs away from a disk like a pale brushstroke. It is thicker near its base. It narrows as it extends. The narrowing is a density gradient. Along the tail, faint dust lanes appear as even darker threads. The threads twist slightly. They reveal that gas, unlike stars, can compress and cool. Gas can form thin filaments. Those filaments can bend and fold under tidal shear. Shear is not introduced as a new term. It is shown as stretching along a direction. The gentle mechanics remain simple. Stretching makes filaments longer. Compression makes them denser. The section now reaches its limit of observation passage. Predicting the exact shape of tidal tails requires knowing three-dimensional geometry. The line of sight hides depth. The disks have unknown tilt relative to the orbit. The halo shapes are uncertain. A small change in halo shape changes how quickly tails wrap. A small change in pericenter distance changes how much material is lifted. Simulations can explore possibilities. Simulations still depend on assumptions about gas physics and dark matter distribution. Observations of distant halos are faint and incomplete. The tails are easier to imagine than to measure far in advance. This limit is specific. It is about geometry and about model dependence. It does not weaken the main truth. Tides sculpt edges first. Close passes draw tails. Repeated passes deepen the reshaping. The section ends by returning to calm continuity. Even as tails form, most stars remain far apart. The encounter is a rearrangement of orbits and streams. The next section moves closer to the first pass itself. It follows what happens as the two disks begin to overlap, and as the brightest structures start to blur into one evolving system. A first meeting between galaxies is less a moment than a long passage through overlapping space. The first close pass reshapes the disks mainly by stirring gas and bending orbits. The approach has already been framed as inevitable. Now the scene moves toward the threshold where faint tides become visible distortions. At this distance, the disks still look like separate islands. Their halos have already mixed. Their outer streams have already been tugged. The first small unlock arrives early. Even at closest approach, most stars do not strike anything. The main changes come from gravity and from gas because gas can compress. The visual anchor opens on a spiral disk seen from above. The disk has a bright center. The arms are broad. Dark dust lanes lace the arms with soft shadows. Along the outer rim, the light fades into a thin gradient. Near one side of the rim, the gradient looks slightly thicker. The rim appears drawn outward into a faint extension. The extension is not a new arm. It is the beginning of a tidal bridge. It is a faint band of material being pulled toward the partner. The band is uneven. It has a brighter spine and a softer edge. The softer edge suggests material spreading out in depth. The section holds to three concepts. The first is pericenter, the closest approach. The second is tidal bridge, a connecting stream of material. The third is shock, a compression fronting gas. A shock is a sudden rise in density and temperature. The definition stays short. It happens when gas flows converge faster than the sound speed in that gas. The 1-2-1 rule stays calm. A pile-up on a highway creates a dense region that travels backward. A shock is a dense region that travels through gas. It matters because it changes gas structure quickly even when stars remain far apart. The narrative remains free of human elements. The highway image is only a comparison of flow. The scene returns to the pair. As the galaxies near pericenter, the gravity field between them steepens. Orbits in both disks feel a changing pull. The pull is not uniform across each disk. The near side feels more, the far side feels less. This difference stretches the outer disk. It also tilts some orbital planes. The stretch can draw out a long tail. The tilt can warp the disk. Warps look like a gentle bend in a flat sheet. A physical detail appears. The disk's mid-plane is no longer a clean plane. One side rises slightly above the other. The dust lane normally tracing a smooth curve becomes kinked. The kink is not sharp. It is a subtle change in curvature. It is an early sign that the disk is being torqued. Torque is not named as a term. It is shown as a twist. A small payoff lands here. The first pass can create a warp without breaking the disk. The disk becomes a bent sheet rather than a shattered one. The section's main number arrives with care. At first pericenter, the closest distance between the bright centers may be on the order of 100,000 light-years, like two wide lantern glows overlapping without their cores touching. The comparison keeps it soft. It also sets a scale shift. 100,000 light-years is far larger than the size of a single star's domain. It is closer to the span of a galaxy's visible disk. This scale explains why the encounter is a broad overlap rather than a pinpoint hit. Within that broad overlap, gas behaves differently from stars. Stars follow collisionless orbits. They pass through with little direct interaction. Gas clouds can collide. When gas streams from both galaxies meet, shocks form. The shocks compress gas into thinner layers. The layers can become dense sheets. Dense sheets can fragment into knots. The knots are clumps of gas, not separate galaxies. Their edges can be sharp compared to the surrounding haze. The sharpness is physical. It comes from compression. Dust thickens in the compressed zones. Dust makes shadows deeper. A visual anchor returns to a dust lane that becomes a dark ridge. The ridge runs along a curved arm. Near the ridge, the background glow looks brighter on one side. That brightness difference suggests the ridge sits in front of a bright layer. The ridge is a boundary between layers. This is another small unlock. A galaxy's disk is layered. Dust marks where layers overlap and where compression concentrates material. The encounter makes those layers fold. It makes them overlap more strongly. The fold can create a temporary bright arc. It can also create a temporary dark seam. The seam is a thicker dust layer. The seam is a moving shadow. The story now reaches a limit of observation passage. Predicting the exact geometry of the first pass is uncertain. The sideways motion is hard to measure with perfect precision. The halo's shapes are not mapped directly. The disk's tilts relative to the orbit are uncertain. Small differences change where bridges form. They change whether a bridge is prominent or faint. They change whether a tail is long or short. Simulations explore many possibilities. Simulations depend on assumptions about gas cooling and feedback. The limitations are specific. They involve geometry resolution and model choices. Yet the broad outcomes are robust. A close pass produces warps. It produces tidal bridges. It produces shocks in gas where streams meet. These features are expected even if their exact shapes vary. The section returns to calm motion. During and after pericenter, the galaxies do not stop. They pass through and continue on altered trajectories. Their centers swing apart again for a time. The tails and bridges remain as lingering structures. The bridge can thin and fade. The tail can broaden and wrap. The disk can settle partially, then warp again on the next approach. Another small payoff settles in. The first pass does not finish the merger. It sets the pattern. It rearranges orbital energy and angular momentum. It also feeds dynamical friction by creating wakes in the halos. The wake slows the pair over time. The pair loses orbital energy gradually. The next pass becomes closer. The next pass becomes more disruptive. The visual anchor closes on the bridge, now stretched and faint. It is a dim ribbon between two bright ovals. It has a brighter spine and a soft edge. It is not a firm connection. It is a transient flow. Its existence shows how gravity can draw matter across vast gaps without any hard contact. The section ends with a gentle transition. After the first pass, separation returns briefly, but the system is no longer the same. The next section follows the aftermath, where tails expand, disks warp further, and repeated encounters begin to blur two galaxies into one evolving structure. After a close pass, space looks wider, yet the system is already more tightly bound. The galaxies swing apart briefly, and the return is set by lost orbital energy. The first small unlock is calm. Separation after the first pass is not escape. It is the long arc of a shrinking orbit. The visual anchor opens on two distorted spirals drifting away from each other. Each disk is no longer a clean oval. Each has a slight bend. A tidal tail trails behind like a pale brushstroke. The tail is thicker near the disk. It thins and fades outward. The fading is a density gradient. It is a physical signature of material spreading along many similar paths. Between the galaxies, the earlier bridge has stretched and weakened. It looks like a faint strand of haze. Its edges are soft. Its center is slightly brighter. The strand is not a rigid connection. It is a flow that is thinning as gravity reshapes it. The section holds to three concepts. The first is orbital energy. The second is dynamical friction. The third is phase mixing. Orbital energy is the energy of motion and position in gravity. It is not a new kind of energy. It is a bookkeeping tool that predicts whether an orbit stays bound. Dynamical friction has already appeared as gravitational drag. It now becomes the main driver of the shrinking return. As the galaxies move through each other's halos, they raise wakes. The wakes are subtle overdensities in dark matter and stars. The overdensities lag behind. Their gravity pulls backward. The pair slows slightly at each pass. This is the second small unlock. The halos act like a gentle braking medium, even though it is almost empty in light. The analogy for this section arrives quietly. The orbit resembles a pendulum that loses a tiny bit of swing each time through the middle. The pendulum image is unique here. It emphasizes repeated motion and gradual loss without any sharp event. The swing outward is real. The swing back is also real. The amplitude shrinks because energy is transferred to the surrounding halo. That transferred energy does not vanish. It becomes extra motion in the halo's particles. It becomes heat in a gravitational sense. It makes the halo slightly puffier. It can blur some fine structures. Phase mixing is the third concept. Phase mixing is the smoothing of coherent streams over time. The definition stays short. A group of stars pulled into a tail begins with similar orbits. As time passes, small differences in orbital periods spread them out. The tail becomes broader. The bright spine softens. The edges become more diffuse. This is a small payoff. Tidal tails can look sharp at first. They become gentler as orbits drift out of step. The visual anchor returns to a tail that begins to feather at the edges. The feathering is a soft fringe of faint light. It is not a new component. It is the same material now spread over a wider region. The feathering is a physical detail tied to orbital periods. A slightly faster orbit pulls ahead. A slightly slower orbit lags behind. Over time, the tail becomes a wider ribbon. Some sections of the ribbon show faint ripples. The ripples can come from clumps that form briefly in denser gas. The gas component is thinner than the stellar component. It responds by compressing in places and rarefying in others. Dust appears again as a soft, dark seam within brighter haze. Its seam is not continuous. It breaks into patches. Each patch has a blurred edge because the dust layer is thin and uneven. The number for this section appears with care. The time between the first pass and the next closer return is on the order of a couple of billion years, like a long season that repeats only a few times before settling. The comparison stays gentle. It reinforces deep time. It also creates a scale shift. In a second, a wave on a pond travels a short distance. In billions of years, an orbit completes a slow loop and returns for another pass. The loop is not identical. Each return happens with less orbital energy. Each return happens deeper in the combined gravity field. Another small unlock follows. The merger proceeds by repetition. It is a process of passes and settling. It is not a single event. The aftermath of the first pass also reshapes the disks internally. Warps can persist. The midplane can tilt differently at different radii. The disk can become slightly thicker. The thickening comes from stars gaining vertical motion as tidal forces perturb their orbits. The thickening is a physical detail. The disk's edge looks less razor-thin. Its light profile becomes rounder above and below the plane. Dust lanes can look less orderly. The lanes can bend. They can split. Their shadows can appear in unexpected places because the disk is no longer a simple sheet. The section now reaches its limit of observation passage. Predicting the exact appearance of the aftermath depends on details that are difficult to constrain. The initial tilt of each disk relative to the orbital plane matters. The distribution of gas matters. The halo's shape matters. Even small companions can perturb tails and thicken streams. Observations of other interacting galaxies provide examples, but each system is different. Simulations can match broad features. Simulations still require assumptions about how gas cools and how it forms dense knots. The limitation is specific. It is about sensitivity to initial geometry and to faint, hard-to-measure halo structure. The broad outcome remains stable. Tails form, tails fade, orbits shrink, halos absorb energy. The system moves toward a second closer encounter. The visual anchor shifts to the space between the galaxies. The earlier bridge has become almost invisible. Only a slight haze remains. The haze is not uniform. It has a faint gradient that thickens toward each galaxy. This gradient is a physical sign of overlapping halos and lingering debris. The gradient is also a soft cue. The galaxies are not cleanly separate anymore. Their outskirts have already exchanged material. Their halos have already shared energy. Their smaller companions have already had their paths altered. Another small payoff settles in. Even if the bright disks pull apart, the combined system is already one in gravitational terms. The edges are interwoven. The future is a sequence of deeper overlaps. The section ends with a calm transition. The next pass comes not as a surprise, but as the natural return of a pendulum that has lost some swing. The next section moves into the mechanisms that make the second encounter more transformative, as gas compression and orbital scrambling begin to erase the original spiral order. A spiral pattern can survive one disturbance, then soften under repeated stirring. The second encounter scrambles disk order by mixing orbits and compressing gas into new layered structures. The first small unlock arrives early. A spiral does not need to be torn apart to be erased. It can be blurred into a smoother shape by many small orbital changes. The visual anchor opens on a disk that no longer looks flat. Its midplane bends gently. Dust lanes no longer trace clean curves. They appear as broken seams. Some seams overlap. Some seams cross at shallow angles. The light in the disk shows uneven patches. The patches are not sharp points. They are broad regions with soft edges. A faint tail remains in the outskirts, now thicker and more diffuse than before. Its boundary is a gradient rather than a line. The section holds to three concepts. The first is violent relaxation. The second is angular momentum. The third is gas inflow. Violent relaxation is rapid orbital reshuffling and changing gravity. The definition stays short. It happens when a system's gravitational potential changes quickly. Orbits that were regular become mixed. The word violent sounds harsh, but the process is quiet in sensation at galactic scale. It is a description of speed relative to orbital times. The 1-2-1 rule keeps it calm. A shaken box of fine sand quickly loses neat layers. In a galaxy, changing gravity quickly loses neat orbital families. It matters because it turns a disk with spiral order into a rounder, thicker distribution. Angular momentum is the second concept. It is the tendency of rotating matter to keep rotating. It is not a force. It is a conserved quantity that guides how rotation is redistributed. In an encounter, angular momentum can be transferred outward. Some material gains it and moves to larger radii. Some loses it and drifts inward. This is the second small unlock. A merger does not simply blend two disks. It also moves rotation around inside the combined system. The visual anchor returns to dust seams. Near the center, the glow becomes brighter and more compact. The brightness gradient steepens. The center looks more concentrated than before. Around it, a faint ring-like structure appears in gas and dust. The ring is not perfectly circular. It is slightly lopsided. One side is thicker. One side casts a deeper shadow. The ring is a physical detail tied to inflow and compression. Gas inflow is the third concept. Tidal torques and shocks remove angular momentum from gas. The gas then flows inward. It does not need to fall straight. It can spiral inward along lanes. It can pile up into a dense ring. It can then fragment into knots. The knots are dense gas clumps. Their edges can be sharper than the surrounding haze. The knots are small compared to the whole galaxy. Their effect can still be large because they change pressure and cooling in the inner region. Small payoff follows. Payoff. Stars mostly pass by each other. Gas does not. Gas collides with gas. Gas forms shocks. Shocks compress gas into layers. Layers cool and become thinner. Thin layers are easier to compress further. This chain is how the inner structure becomes more compact after repeated passes. A new visual anchor arrives. Two disks overlap more deeply than before. Their arms are no longer distinct. The overlap region looks like a braided fog. Within the fog, faint linear features appear. They are dust filaments. They align briefly, then bend. They look like dark threads suspended in milky light. The threads indicate shear stretching gas in one direction, while compressing it in another. Shear is not named. It is shown as a pulling motion that turns patches into streaks. The physical detail remains in gradients and layers. The overlap creates layered sheets of gas. Sheets create seams of dust. Seams create shadows. Shadows reveal where material is thickest. The section's main number arrives with care. The orbital period in the outer disk of a large spiral can be a couple of 100 million years, like a slow season that repeats only a few times across the whole encounter. The comparison stays gentle. It also creates a scale shift. In a second, a small eddy in a stream forms and dissolves. In hundreds of millions of years, an orbit completes one full turn, and the gravity field has time to change again. When the potential changes on a similar timescale orbits are strongly perturbed, this is where violent relaxation gains meaning. The gravity field during the second encounter changes more rapidly than during the first. The galaxies are closer. The mass overlap is deeper. The wake in the halos is stronger. The orbital energy is lower. The pericenter is tighter. The changing potential mixes orbits. It thickens the stellar distribution. It reduces the clarity of a single disk plane. Another small unlock lands here. A disk can survive as a structure while losing its spiral memory. It becomes a thicker, smoother rotating body. The rotation remains because angular momentum is not destroyed. It is redistributed. Some goes outward into tails and extended halos. Some remains in the center as a faster, denser rotation. The lopsided ring-like feature can appear because inflow is not perfectly symmetric. It follows the geometry of the encounter. It can be offset. It can be warped. It can break into arcs. The arcs can merge again. The section now reaches its limit of observation passage. Predicting the exact internal outcome depends on gas physics that is difficult to model perfectly. Cooling rates depend on composition. Fragmentation depends on turbulence. Shocks depend on relative velocities that vary with geometry. Even the amount of inflow depends on how bars or spiral distortions develop during the pass. Bars are not introduced as a term. The idea is shown as an elongated central distortion that funnels gas. Observations of interacting galaxies show a wide range of central structures. Simulations can reproduce many. The limitations remain specific. They involve resolution turbulence and uncertain initial conditions. Yet the broad pattern is stable. Repeated encounters mix orbits. Mixing thickens disks. Gas loses angular momentum and flows inward. Inflow steepens the central brightness gradient. Spiral arms become harder to recognize. The visual anchor closes on the thickened disk. The outer rim is now less crisp. The halo glow looks slightly more prominent relative to the disk. Tails are still present but more diffuse. They resemble long fading brushstrokes rather than sharp ribbons. The center holds a denser core. Around it dust and gas form layered seams and partial rings. The system looks less like two separate spirals. It looks more like one disturbed evolving mass with two bright concentrations moving within it. The section ends with a gentle transition. The next section follows how the two bright centers finally lose their separate paths and sink into one common core as dynamical friction completes its slow work and the remnant begins to settle. Two bright centers can orbit each other for a time, then quietly become one. The final sinking happens because the surrounding halo carries away orbital energy and angular momentum. The first small unlock arrives early. The merger's decisive step is not a sudden impact. It is the slow loss of a separate orbit. The visual anchor opens on a disturbed system with two luminous concentrations inside a shared haze. The haze is thickest near the middle. It fades outward with a smooth gradient. Around the pair, faint tails still arc away. They are broader now. Their edges are feathered. Near the inner region, dust no longer lies in neat lanes. It appears as mottled patches. Some patches form short curved seams. The seams overlap. Their shadows are soft because layers are stacked in depth. The scene feels like a stormless cloud of starlight with two denser cores drifting inside. The section holds to three concepts. The first is dynamical friction. The second is core pairing. The third is relaxation. Dynamical friction remains the gentle drag from gravitational wakes. It becomes stronger as the pair moves through denser regions of the combined halo. Core pairing is the stage where the two dense centers orbit closely inside one potential. The definition stays short. It is when the pair becomes a bound binary within the remnant. Relaxation is the slow settling of orbits toward a smoother distribution. It is not a perfect stillness. It is a trend toward equilibrium. The first small payoff follows quickly. A core pair can orbit many times while the larger system looks almost unchanged from far away. The change is inside. The wakes are inside. The energy transfer is inside. The visual anchor tightens. The two cores leave faint trails of disturbed density behind them. The trails are not visible light streaks. They are slight enhancements in the surrounding halo. If the halo were seen as a fog, the fog would be a little thicker behind each core. The thickness is the wake. The wake pulls backward. It drains orbital energy. It also drains angular momentum from the orbit of the pair. The drained angular momentum is not destroyed. It is carried outward into the halo as extra random motion. This is another small unlock. The remnant becomes rounder, partly because the halo is stirred by the sinking cores. The core orbit shrinks. The orbital speed rises. The pericenter becomes less meaningful because the orbit becomes more circular and more confined. The surrounding potential also changes. It becomes deeper near the center as mass piles inward. Gas inflow from earlier shocks has already built a denser inner region. Some of that gas can settle into a rotating central structure. The structure can be thick, it can be clumpy, it can also be turbulent. Turbulent is not used as a technical term here. It is shown as irregular motion that blurs clear lanes. Dust patches are a physical detail. They mark dense gas pockets. These pockets cast deeper shadows. Their edges are still soft because dust is mixed with stars in a layered region. Another visual anchor arrives. A faint oval envelope surrounds the system. The envelope has smooth isophotes like nested contours of brightness. The contours are not perfectly centered on either original galaxy. They are centered on the combined mass. The envelope looks more like an early elliptical shape than like two spirals. The spiral arms are gone as coherent patterns. The disk planes are no longer distinct, yet some rotation remains. It appears as a gentle flattening of the inner light distribution. The flattening is subtle. It suggests that not all angular momentum has been randomized. This is a small payoff. A merger remnant can be round overall and still retain a faint memory of rotation in its shape. The section's main number arrives with care. Once the cores are within a few thousand light years, the final coalescence can happen in a few 100 million years, like a slow closing of a gap that seems to vanish only at the end. The comparison stays calm. It also creates a scale shift. In a second, a drifting speck crosses a small distance. In hundreds of millions of years, a massive core pair loses its separate orbit and becomes one center. The number is rounded. The phrasing stays spoken and simple. The sequence continues. As the cores sink, their wakes overlap. The overlapping wakes deepen the drag. The pair tightens. Each orbit takes less time. The energy loss per orbit can remain small. The cumulative effect becomes decisive. The remnant's inner region becomes denser. The outer tails continue to expand. They continue to fade. Their material begins to phase mix into the halo. Fine features blur. The halo grows smoother. The brightness gradient becomes more regular. The physical details shift from sharp lanes to soft contours. This is another small unlock. Mergers trade sharp structure for smooth structure. They replace distinct disks with a single envelope of light. The section now reaches its limit of observation passage. The inner dynamics are hard to reconstruct from outside because the deepest regions are complex. Dust can hide central light. Overlapping layers can confuse true shapes. The line of sight compresses a three-dimensional structure into a two-dimensional image. The remnant's mass profile must often be inferred from motions. Motions in the center are difficult to measure cleanly at great distance. Models can match the overall envelope. Models can still disagree on details of the inner density cusp and the remaining rotation. The limitation is specific. It is about depth obscuration and projection. It does not change the broad picture. Two cores sink by dynamical friction. The remnant relaxes toward a smoother form. The system transitions from a pair to one. The analogy for this section arrives now. The sinking resembles two leaves circling in a slow eddy, then settling into one shared swirl as the eddy widens and loses definition. The image is unique here. It suggests gentle motion and gradual merging. It also keeps the tone quiet. The leaves do not collide in a sharp way. They circle. The water carries away their separate paths. The visual anchor returns to the nested contours of the envelope. The outermost contours are faint. They fade into black with a smooth gradient. The inner contours are brighter and more compact. The center is now single. The tails are still present, but they are faint arcs that blend into the halo. Dust patches remain in the inner region as soft shadows. Over time, even these shadows can thin as gas is consumed or dispersed. The remnant's light becomes more uniform. The shape becomes steadier. The next section widens the view again. It follows where the strip material goes, how the halo grows, and how the local group's smaller members respond to the new larger gravitational center. A remnant can look settled at the centre while its outskirts keep drifting for ages. The merger grows a larger halo as tidal debris spreads and phase mixes into a smooth envelope. The first small unlock arrives early. The remnant's outer edge is not a wall. It is a slow gradient where debris becomes part of the halo. The visual anchor opens far from the new centre. The light is extremely faint. It is a broad round glow that fades outward with a gentle slope. Within that glow a few arcs appear. They are wide and soft. They are former tidal tails now blurred into shell-like curves. A shell edge looks slightly brighter because many orbits pile up there. The edge is not sharp. It is a thin enhancement on top of a smooth background. The physical detail is a boundary created by orbital crowding. It is like a faint contour line in fog. The section holds to three concepts. The first is phase mixing. The second is shell structure. The third is escape speed. Phase mixing has appeared before as the spreading of coherent streams. It now becomes the main mechanism for turning debris into halo. Shell structure is a curved edge where stars linger at turning points. The definition stays short. It forms when many similar orbits reach apocenter at similar radii. Escape speed is the speed needed to leave a system's gravity. The definition stays short. It depends on the mass distribution and distance from the centre. The narrative stays calm by focusing on turning points. As debris is pulled into tails, some becomes unbound. Some remains bound on long elongated orbits. The bound material swings out to large radii, then returns. At apocenter, its speed is lowest. It spends more time there. This timekeeping effect creates shells. This is the second small unlock. Shells are not solid walls. They are places where orbits pause briefly, making light slightly denser. The visual anchor lingers on a shell edge. It curves like a shallow arc of frost on dark glass. The arc is brighter along a thin ridge. It fades on both sides. The fading is gradual. It marks a change in orbital density, not a physical surface. Nearby, a second arc lies farther out. It is fainter. It has a wider edge. These nested arcs suggest multiple generations of debris. Each generation comes from a different pass. Each has a different orbital energy distribution. The arcs are quiet records of time. They also set up a scale shift. A single orbit of a star in the outskirts can take hundreds of millions of years. Over a few billion years, the same star can complete only a handful of such loops. In a second, light crosses a small distance. In a billion years, debris completes a slow breathing motion in and out of the halo. This breathing is not rhythmic like a clock. It is the natural pacing of long orbits. The section's main number appears with care. The new halo can extend more than 1 million light-years across like a dim lantern glow that fills a vast room beyond the visible flame. The comparison keeps it soft. It also makes the scale legible. 1 million light-years is far beyond the bright central body. It is a region where the night looks almost empty, yet gravity remains organized. Another small payoff lands here. The remnant is not only a bright central galaxy. It is a large gravitational field with a faint extended light component built from debris. Escape speed enters the story gently. At a given radius, some debris travels fast enough to escape. Some does not. The boundary between bound and unbound is not a sharp line. It depends on direction and on where the debris is launched in the encounter. The unbound fraction can carry away angular momentum. It can also carry away energy. This helps the remnant settle. The bound fraction becomes halo material. It thickens the envelope. It increases the roundness of the outer light profile. Another visual anchor appears. A long tidal tail has faded into a broad ribbon. Its spine is no longer clear. Instead, a wide fan of faint light spreads outward. The fan has a subtle gradient. It is brighter near the remnant. It fades with distance. Within the fan, slight ripples appear. They are density waves in the debris, not waves in a fluid. They come from phase wrapping. Phase wrapping is not named. The idea is shown as debris with slightly different orbital periods that overlaps in radius. creating alternating regions of slightly higher and lower density. The ripples are faint. They're easy to lose in background noise. This leads to the limit of observation passage. Detecting halo substructure requires extraordinary sensitivity. The surface brightness is extremely low. Foreground stars in the same line of sight can mask features. Background galaxies can confuse the faint glow. Dust within the remnant can create patchy extinction that mimics ripples. Even when arcs are seen, converting them into a three-dimensional mass map is difficult. The arcs depend on projection. Their curvature depends on viewing angle. Models can fit arcs with families of orbits. Different models can match the same arcs. The limitation is specific. It is about low contrast projection and degeneracy in modeling. Yet the broad truth stands. Tidal debris spreads, it phase mixes, it forms shells and smooth halo light over time. The section returns to escape speed with a gentle image. Imagine tossing fine powder into still air. Some grains fall back. Some drift away through a doorway. The doorway is not visible from the grains. It is defined by airflow and openings. In gravity, the doorway is defined by energy. Some debris has enough to leave, some does not. The analogy stays unique. It remains quiet. It avoids impact. It emphasizes sorting rather than violence. Another small payoff follows. The halo grows from both mixing and sorting, mixing smooth structures, sorting separates bound from unbound. Together they set the remnant's outer profile. The local group environment also responds. Smaller galaxies that once orbited the Milky Way or Andromeda find themselves in a new combined potential. Their orbits can expand or shrink depending on energy exchanges. Some may be captured into longer, more eccentric paths. Some may be thrown farther out. These changes are slow. They occur over long times. Their signatures can be subtle streams and arcs around the remnant. The visual anchor closes on the outer halo again. The nested arcs are now fainter. Their ridges are softer. The background glow is smoother. The gradient from center to edge is gentle and continuous. The remnant looks like a single calm structure surrounded by an enormous, almost invisible envelope. The next section moves from the remnant's outskirts to its overall classification. It follows how the merged system resembles an elliptical-like galaxy, how its light profile settles, and how rotation and anisotropy balance in the final shape. A galaxy can change its shape without changing its mass simply by rearranging the orbits that hold it up. The merged remnant settles into a smooth elliptical-like body as orbital families mix and the light profile becomes regular. The first small unlock arrives early. An elliptical appearance does not mean a lack of structure. It means structure has become statistical spread across many directions of motion. The visual anchor opens on the remnant from a great distance. The central glow is bright and compact. Around it lies a broad envelope of faint light. The envelope has nested contours that look like soft ovals. Each oval is slightly larger than the next. The spacing between them changes gently. Near the center, the brightness drops quickly with radius. Farther out, the drop becomes more gradual. This is a physical detail. It is a gradient in surface brightness that reflects how stars are distributed in depth. A faint dust shadow remains near the core. It is not a lane. It is a diffuse patch. Its edge is blurred, suggesting a thin veil rather than a thick band. The section holds to three concepts. The first is anisotropy. The second is virial equilibrium. The third is isophote. Anisotropy is direction-dependent orbital motion. The definition stays short. It means stars move differently along different axes. Virial equilibrium is a balance between motion and gravity. The definition stays short. It is the state where average kinetic energy matches the gravitational binding in a stable way. An isophote is a line of equal brightness. The definition stays short. It is a contour traced through an image of light. The narrative uses these ideas without becoming technical. In a disk, many stars share a preferred plane. Their orbits have a strong directionality. In a relaxed remnant, the preferred plane is weaker. Orbits point in many directions. Some are still more common than others. The remnant can still rotate. It can still be slightly flattened. Yet the distribution is no longer a thin sheet. This is the second small unlock. Elliptical-like does not mean spherical. It means the body is supported by a mix of orbital shapes. Some orbits are boxy, some are loop-like. The terms are not emphasized. The images are. Some paths wander closer to the center, then swing out. Others circle around a common axis. Together they build a smooth envelope. The visual anchor shifts closer. The isophotes are not perfect ellipses. At some radii they look slightly box-shaped. At others they look slightly pointed. These subtle deviations are physical. They can reveal anisotropy and remaining rotation. A boxy isophote suggests more stars on box-like orbits. A pointed isophote suggests different orbital weighting. The remnant's envelope is like a softly moulded clay form. This is the section's unique analogy. The clay is not shaped by a single stroke. It is shaped by many gentle presses. Each press is a past orbit. Each press leaves no sharp mark. Together they create a smooth contour. Another small payoff arrives. The light profile becomes a record of how thoroughly the remnant has relaxed. A steep central gradient suggests a dense core. A shallower outer gradient suggests an extended halo and debris that has mixed. The core itself can include multiple components. Some stars come from the original bulges, some come from heated disks, some form from gas that flowed inward during the merger. The formation channel is not listed. It is implied through layering. The faint dust patch indicates that some gas remains, or that dust is left suspended in the inner region. If the dust patch fades over time, the center becomes cleaner in light. The outer envelope remains. Its contours become more regular. Virial equilibrium enters gently. As the potential stabilizes, the remnant's global properties change slowly. The average speeds of stars balance the depth of the gravitational well. The system stops undergoing large rapid potential changes. Orbital mixing continues but more gradually. This is a small unlock. Relaxation has phases. Early phases are fast because the potential changes quickly. Later phases are slow because the potential is steadier. The section's main number appears with care. A typical star in the inner tens of thousands of light years can complete an orbit in a few 100 million years, like a slow clock that ticks only a few times across a billion-year span. The comparison stays soft. It also creates a scale shift. In seconds, light travels far relative to a planet. In hundreds of millions of years, a star completes one loop in a galaxy-scale potential. Over many loops, the memory of initial placement fades. Phase mixing smooths remaining streams. Isophotes become cleaner. Shells in the outskirts become harder to see. The remnant begins to look more like a single settled object. Anisotropy remains important because it controls shape. If motion is more random in all directions, the remnant is rounder. If motion retains a preferred axis, the remnant is flatter. The difference can be subtle. It can appear as a slight elongation of isophotes. It can appear as a gentle twist of isophotes with radius. A twist is a physical detail. It suggests that different radii have different preferred axes. That can happen if debris with different angular momentum settles at different depths. The visual anchor lingers on a slow twist. The inner oval is oriented one way. The outer oval is rotated slightly. The change is gradual. It is almost like a slow turning of a compass needle. The needle is not present. The image is only the turning of contours. Another small payoff arrives. A twist in isophotes is a quiet sign that the remnant keeps layered memories of how it was assembled. The section now reaches its limit of observation passage. Classifying a remnant as elliptical-like depends on what can be measured. At low surface brightness, the outer envelope is difficult to trace. Background noise can swallow faint contours. Foreground stars can contaminate the light profile. Projection can hide true three-dimensional shape. A remnant that is slightly flattened can look round from some angles. A twist can be mistaken for a separate component if the image is shallow. Kinematic measurements are also hard at great distance. Motions are inferred from spectral features that blur when signal is weak. The limitation is specific. It is about surface brightness viewing angle and the challenge of measuring stellar motions far from the center. Still, the broad outcome is stable. A major merger of two large spirals tends to produce a smoother, thicker remnant with elliptical-like appearance. The clay analogy returns gently. Over time, the form keeps its mass but loses sharp edges. Spiral arms are sharp edges in light. They fade as orbits mix. Dust lanes are sharp edges in shadow. They fade as gas is consumed or dispersed. The final result is a body of layered gradients: bright center, smooth envelope, faint outskirts. The visual anchor closes on the outermost isophotes. They are barely visible. They curve gently and fade into darkness. The remnant appears calm and unified. The next section steps outward again into the broader local group. It follows how other galaxies respond to the remnant's new mass distribution, how satellite orbits shift, and how the group itself continues its slow gravitational choreography. A small companion galaxy can feel a merger's pull long before it ever comes close. The local group's satellites shift their orbits as the combined mass center forms and the outer halo grows. The first small unlock arrives early. Satellites do not orbit a visible disk. They orbit the full mass distribution, including the extended halo. The visual anchor opens on the remnant and its surroundings as a quiet field of faint points and smudges. The remnant sits near the center as a smooth glow. Around it, small dwarf galaxies appear as tiny diffuse knots. Some knots have faint tails of their own, some have no tails. Between them, thin stellar streams curve like pale threads. The threads are not straight. They arc gently. Their brightness is uneven. One segment is slightly thicker. Another segment fades into nothing. The physical detail is a stream with a gradient in thickness and a soft boundary. It suggests material that has been stretched and thinned. The section holds to three concepts. The first is tidal radius. The second is pericenter. The third is group potential. Tidal radius is the boundary where external tides overcome self-gravity. The definition stays short. It marks how far a satellite can hold onto its own stars. Pericenter is the closest approach in an orbit. The definition stays short. It is where tides and speeds peak. Group potential is the combined gravitational field of the local group. The definition stays short. It is the landscape that guides all satellite paths. The narrative stays calm by following one satellite-like knot at a time. A satellite moves along its orbit through the group potential. As the remnant forms, the potential deepens near the center. It also becomes smoother in shape because two large centers become one. Orbits that once circled one host can shift. Some satellites that once belonged to Andromeda can now pass closer to the merged center. Some that once belonged to the Milky Way can now find their apocenters altered. This is the second small unlock. Satellites can be reassigned without being captured violently. A changing potential can gently change which center dominates their motion. The visual anchor tightens on a thin stream. The stream is the satellite's former outer layer. It stretches into a long arc. The arc has a leading arm and a trailing arm. The two arms are not named as such. They are shown as two threads departing in opposite directions along the orbit. One thread is slightly brighter near the satellite. The other is fainter and more diffuse. The difference is a physical detail tied to orbital history. The inner parts of the satellite remain bound. The outer parts cross the tidal radius and drift away. Tidal radius enters as an image. Imagine a small island in a rising tide. The shoreline retreats. The island still exists, but its outer sand is carried off. This is the section's unique analogy. It is quiet. It is familiar. It matches the idea of a boundary that moves with conditions. The island is the satellite. The tide is the group's changing pull. Another small payoff follows. The tidal radius is not fixed. It shrinks near pericenter. It expands near apocenter. A satellite can lose material in pulses timed by its orbit. That timing is slow. It is measured in hundreds of millions of years. The section's main number appears with care. A typical satellite orbit around the group can take a few billion years, like a long wandering loop that completes only a few times over the age of large galaxies. The comparison stays soft. It also creates a scale shift. In seconds, dust can settle in still air. In billions of years, a dwarf galaxy completes a single path around a group-scale potential. This slow pacing matters because the merger unfolds over similar spans. A satellite can experience the merger as a series of gently changing conditions rather than as a single event. Pericenter becomes important because it sets the strongest tidal episodes. At pericenter, the satellite's speed is highest. The surrounding density can be higher. The tidal gradient across the satellite becomes stronger. The satellite's outer layers can be pulled into streams. Those streams can wrap around the remnant. They can also intersect older streams. Where streams overlap in projection, the light can look thicker. In depth, the streams can be far apart. This leads to the limit of observation passage. Streams are difficult to map because they are faint and three-dimensional. A single line of sight can stack multiple streams. A stream's apparent thickness can be an illusion of projection. The distance along a stream can be hard to infer without precise measurements. Models can fit a stream with many different orbits if the distance profile is unknown. The limitation is specific. It is about distance uncertainty, projection degeneracy, and low surface brightness. Yet streams still teach stable lessons. They trace the group potential. They reveal past perienters. They show where tidal radius was crossed. Another visual anchor arrives. Several dwarf knots sit along a broad plane-like arrangement. The arrangement is not a literal flat sheet. It is a preferred region in space where satellites cluster. Its edge is fuzzy. Its thickness is large. This plane-like pattern is a physical detail that can arise from accretion along filaments or from group history. The script does not insist on one cause. It stays gentle. A small payoff arrives. Even if satellites appear to align, their orbits can still be diverse. Apparent planes can be temporary. They can be shaped by selection. They can be reshaped by the merger as the mass center changes. Group potential returns as a landscape. Imagine a broad valley whose lowest point slowly shifts as two hills settle into one. The valley floor is where the remnant center becomes most dominant. Small marbles rolling in the valley would adjust their paths. This is an image, not a human scene. It remains quiet and physical. The marbles are only an analogy for satellites. It emphasizes that the orbit responds to the shape of the potential, not to the visible light alone. The visual anchor returns to the remnant's outer halo. The halo's faint glow now contains multiple curving threads. Some threads are smooth, some are clumpy. Clumps are denser remnants of satellites. Smooth threads are older streams that have mixed. The boundaries of older streams are softer, their gradients are shallower. The newer streams have slightly sharper edges. Their brightness contrast is higher. Over time, phase mixing will soften them. The group's outskirts remain dynamic. Small companions continue to fall in. Some are stripped early, some survive longer. The remnant's growth continues quietly through these additions. The section ends with a gentle transition. The next section widens further to the local group as a whole. It follows how the group's outer boundary evolves, how expansion beyond the group competes with gravity, and how the merged system sits within the larger cosmic flow. The edge of a galaxy group is not a wall, but a gradual change in who holds what. The local group's boundary becomes a quiet contest between inward gravity and outward cosmic expansion. The first small unlock arrives early. There is a distance where the group's pull matches the general outward drift. Inside that distance, orbits remain bound. Outside, its separation tends to grow. The visual anchor opens on the group as a dim archipelago in darkness. Two larger islands of light have already become one. Around it lies a loose ring of faint companions. Beyond them, the field is emptier. The emptiness is not absolute. It is a slow fade of density. A faint haze of scattered starlight and dark halo matter extends farther than the visible glow. Its edge is soft. Its gradient is shallow. This physical detail matters. A soft boundary makes a group difficult to define by appearance alone. The section holds to three concepts. The first is the turnaround radius. The second is escape speed. The third is the cosmic expansion rate. Turnaround radius is where outward drift and inward pull balance. The definition stays short. It is the scale where motion changes from falling in to moving away. Escape speed is the minimum speed needed to leave a potential. The definition stays short. It is the speed that prevents return. The cosmic expansion rate is how separation grows with distance. The definition stays short. It sets the background drift of space on large scales. The narrative begins with the simplest image. Imagine a gentle slope in snow. A few loose grains sit on the slope. Some grains slowly slide toward a shallow hollow. Others slide away toward lower ground. The grains are not forced. The slope decides. This is the section's unique analogy. It captures a boundary without sharp edges. The hollow is the group potential. The slope is the background expansion. Another small payoff follows. A boundary in gravity can be defined by motion rather than by light. The turnaround radius is not marked by a visible ring. It is marked by the change in typical trajectories. Inside paths curve and return. Outside paths drift outward and do not close. The visual anchor shifts closer to the faint outskirts. A thin stellar stream hangs far from the centre. It is extremely dim. Its ends dissolve into the background. Nearby, a small dwarf galaxy is surrounded by a faint envelope. The envelope is rounder than the dwarf's inner light. The envelope is the outer halo of the dwarf. Its edge is blurred by tides and by the low density of stars. This is a physical detail. It is a boundary where the last bound stars become sparse. The group halo itself also has a boundary, but it is softer still. The main number appears carefully. The turnaround scale for the local group is on the order of a few million light-years, like a quiet domain large enough to hold several copies of the Milky Way to Andromeda distance end to end. The comparison stays gentle. It also creates a scale shift. A single orbit inside a galaxy is measured in hundreds of millions of years. The group boundary is measured in millions of light-years and in billions of years. At this distance, a signal would take millions of years to cross the domain. Motion is slow, change is slower. Cosmic expansion rate enters as background. On very large scales, separation tends to increase. Inside a bound group, the group's gravity dominates. The merged remnant sits at the deepest part of the potential. Satellites nearer in remain bound. Farther out, some objects sit near the turnaround region. Their velocities can be small relative to the group. Their paths can look almost stalled. This is a small unlock. Near the boundary, the group can act like a slow eddy in a river. Objects can linger in a region where net drift is small. The river is only an image. There is no water. It is a way to picture a balance of tendencies. Escape speed becomes a second way to define the boundary. The deeper the potential, the higher the escape speed. In the inner group, escape speed is large. In the outskirts, escape speed falls. A tiny push in speed can decide whether an object returns. This is another payoff. The boundary is sensitive. It depends on both position and velocity. A dwarf at the same radius can be bound if it moves slowly. It can be unbound if it moves faster. The visual anchor lingers on an imagined map of motion without showing any tools. Paths appear as faint arcs. Some arcs loop back. Others arc outward and never return. The difference is subtle. At the boundary, the curvature is gentle. The arcs nearly look like straight lines. The scale shift deepens. In a second, a photon crosses a few 100,000 kilometers. In a billion years, a dwarf galaxy can travel a small fraction of the group's diameter. The group is a slow machine. It changes by tiny increments. It can still change decisively, but only across vast time. The limit of observation passage arrives softly. The turnaround radius is hard to measure because it requires accurate distances and velocities for many faint objects. Distances can have large uncertainties at millions of light years. Velocities can include motions not aligned with the line of sight. The true three-dimensional speed is partly hidden. The group's mass distribution is also uncertain in the outskirts. Dark halo density falls gradually. Small changes in assumed halo shape can shift the inferred boundary. The limitation is specific. It is about distance errors, missing transverse motions, and uncertainty in the outer halo profile. Even with these limits, the picture remains steady. The local group is a bound region embedded in an expanding universe. The merger deepens the central potential. It can pull in some borderline companions more effectively. It can also fling some material outward during interactions. Yet the group boundary remains a zone rather than a line. The snow slope analogy returns. A slightly deeper hollow collects a few more grains. It does not collect everything on the hillside. The hillside is too broad. The grains too scattered. The outward drift still exists beyond a certain range. Another small payoff arrives. The merger changes the center more than it changes the far edge. Deep inside, the remnant reorganizes stars and gas and orbits. Far outside, the same cosmic expansion continues. The boundary shifts, but slowly. The visual anchor returns to the faint outskirts. The density of satellites drops with radius. The sky becomes emptier. Yet a few isolated dwarfs remain barely luminous. Their light profiles are diffuse. Their edges are indistinct. They look like smudges that nearly dissolve. This softness is the physical truth of the group's edge. Nothing ends sharply. The section ends with a gentle transition. The next and final section settles the arc into a calm closure. It gathers the group's motions into a quiet perspective. It lets the merged remnant rest as one structure within a larger, slowly expanding cosmos. A galaxy group settles into its future without a final moment, because change arrives as a slow accumulation. The local group ends as one dominant remnant surrounded by quieter companions. The first small unlock arrives at once. The collision is not a single crash. It is a long sequence of passes and blending guided by gravity and time. The visual anchor opens on a calm dark field where one broad glow replaces two. The glow is not a perfect disk. It is an oval haze with a bright core. Around it, faint shells arc like thin ripples. The shells are real structures. They are layers of stars spread by earlier passages. Their edges are sharp in places and soft in others. A gentle gradient runs across them. Brightness fades outward like breath leaving a surface. This physical detail matters. Shells and streams hold memory of motion long after the motion changes. The section holds to three concepts. The first is phase mixing. The second is a tidal stream. The third is relaxation. Phase mixing is the spreading of orbits into a smooth pattern. The definition stays short. It is how ordered motion becomes a blended distribution over time. A tidal stream is a long ribbon of stars pulled by gravity. The definition stays short. It is a stretched trail from a disrupted companion. Relaxation is the settling toward a stable shape. The definition stays short. It is the slow smoothing of a system toward equilibrium. The story begins at the center. In that region, stars follow many different paths. Some paths are rounder, some are long and narrow. Some plunge close to the core, then swing far outward. Over time, the paths spread in angle. They overlap more completely. The light becomes smoother. The remnant's core looks steady, but only because many motions average together. The section's unique analogy arrives gently. It is like a box filled with fine sand after a careful shake. At first, ridges and small dunes appear. After many small taps, the surface levels. It does not become perfectly flat. It becomes quietly consistent. The ridges are the shells. The taps are repeated gravitational encounters. The leveling is phase mixing. Another small payoff follows. Even when the remnant looks calm, the stars are not still. Calm appearance is created by many moving parts. The visual anchor moves outward to the faintest regions. A single tidal stream curves in a wide arc. It is extremely thin. It is narrower than the remnant's broad halo by a vast margin. Its thickness varies along its length. In a few places it looks braided. The braid is an overlap of slightly different orbital paths. The stream's edge is sharper on one side. It is softer on the other. This is a physical detail. It reflects how stars drift away from the mean path. A slow-scale shift follows. Inside the bright core, a star completes an orbit in tens of millions of years. Far out in the halo, an orbit can take billions of years. The same gravity rules both scales. Time changes how it feels. Near the center, mixing happens faster. Farther out, memory lasts longer. The outer halo can remain textured for a very long time. Shells persist as faint arcs. Streams persist as ribbons. Their persistence offers another payoff. The remnant is not a featureless object. It is a layered record of earlier structure. Some layers are visible as gentle edges. Some layers are too dim to see directly. The group's dwarfs continue to orbit. Some are stripped slightly. Some remain intact. Their own halos are trimmed by tides. The trimming is gradual. The boundaries of those halos are not sharp. They fade with a soft gradient into darkness. In that region, light behaves as a faint tracer of mass. Most mass remains unseen, but its influence remains steady. The limit of observation passage arrives softly and specifically. The faint shells and streams are difficult to map because they are extremely dim. Background light and foreground clutter can hide them. Distance uncertainties blur their true shapes. Velocities are incomplete without transverse components. A stream's thickness can reflect true dispersion or measurement noise. Models of the halo can fit multiple shapes with similar results. The limitation is about low surface brightness, uncertain distances, incomplete velocity information, and degeneracy in mass models. Another small unlock follows. The future collision outcome is robust in broad strokes, even when details remain uncertain. A single dominant remnant forms. A wide halo surrounds it. Some companions remain as satellites. The precise arrangement of shells and streams can differ. The timing of each pass can vary, yet the overall arc stays the same. The local group becomes more internally bound at its center. Its edge remains a soft region where binding fades. The visual anchor widens to include the full group. The remnant sits near the center like a quiet ember. Around it, satellites appear as sparse points. Farther out, the group's matter becomes more diffuse. The boundary is not a line. It is a slow decrease of density and escape speed. The sandbox analogy returns once more without repeating it as a main device. Even after many taps, a few subtle ridges can remain. They are simply smaller. The same is true of the remnant. Relaxation proceeds, but it does not erase every trace. It softens traces until they are faint. The section ends with a gentle landing. No sharp ending appears, only a steady settling. The remnant's glow holds its shape for long spans of time. Beyond it, space continues its wider expansion. The local group remains a quiet island within a much larger sea of distance.